Welcome to lecture number 7. You may kindly recall that in the earlier lectures we had demonstrated the estimation of model parameters beta 0, beta 1 and sigma square using the principle of least square, and we had obtained the direct regression estimates of beta 0, beta 1 and sigma square. Now we use another approach, maximum likelihood estimation, and we demonstrate how to obtain the estimates of model parameters beta 0, beta 1 and sigma square. So we are going to talk about the maximum likelihood estimation. Likelihood estimation of parameter estimation. So you may kindly recall that we had considered the model y I is equal to beta 0 plus beta 1 xi plus epsilon I, and we had assumed that epsilon i's are all IID identically and independently distributed following a normal distribution with mean 0 and variance sigma square. So what's a likelihood function? Likelihood function is nothing but the joint probability density function of all the random variables. So here we have the random variable epsilon, and then with the joint probability density function of epsilon 1, epsilon 2, epsilon n will be the likelihood function of epsilons. So we all know that the probability density function of epsilon I, this is going to be 1 over sigma root 2 pi exponential of minus 1 over 2 epsilon I minus 0 whole square over sigma square. Right. Now when I try to write down the likelihood function is given by f of epsilon 1, epsilon 2, say epsilon n. This is the joint probability density function of epsilon 1, epsilon 2 and up to epsilon n. Since we have assumed that all epsilon i's are independent, so I can write down this joint probability density function as a product of I goes from 1 to n f of epsilon I. So let me connote this likelihood function here as a L, and then the likelihood function can be written as 1 over product of I goes from 1 to n sigma root 2 pi square root of 2 pi exponential of minus 1 over 2 epsilon I square upon sigma square. Right. So this becomes nothing but 1 over sigma square root of 2 pi raised to the power of here n and exponential of minus 1 over 2 summation I goes from 1 to n epsilon I square upon sigma square. Right. The objective in method of maximum likelihood estimation is to obtain the values of the parameters in such a way such that this likelihood function is maximized. So here we want to estimate the 3 parameters beta 0, beta 1 and sigma square, but from this likelihood function you can see that still there is no appearance of beta 0 and beta 1. So I try to write down this likelihood function as a exponential of minus 1 over 2 sigma square I goes from 1 to n, and I try to replace epsilon I by yi minus beta 0 minus beta 1 xi whole square. So now the objective is very simple. I want to maximize this L, which is our likelihood function, and I want to estimate the parameters beta 0, beta 1 and sigma square. And since we know that log function is a monotonic function, that's a monotonic increasing function, so you will see later on that it is easier to handle the log likelihood rather than likelihood function. So at this moment itself, first I can take here log of likelihood, say log of here L, and I am denoting it by here, say this here L star, right. So, and so this is going to be minus n by 2 natural log of 2 pi minus n by 2 log of sigma square minus 1 over 2 sigma square summation I goes from 1 to n y I minus beta 0 minus beta 1 x I whole square. So, now you can see here that this L star, which is the log likelihood, L star is a function of the parameters beta 0, beta 1 and sigma square, right. So, now I try to obtain the value of beta 0, beta 1 and sigma square such that the log likelihood is maximum. So, I use the principle of maxima and minima, for which I find the normal equations like this. Say I will simply partially differentiate the log likelihood function with respect to beta 0, beta 1 and sigma square, right. So, once I try to differentiate it, I get here minus 1 over sigma square summation I goes from 1 to n y I minus beta 0 minus beta 1 x I, and here I get 1 over sigma minus 1 over sigma square summation I goes from 1 to n y I minus beta 0 minus beta 1 x I times x I, and here I get minus n over 2 sigma square plus 1 over 2 sigma square is a square. So, this will become 1 upon 2 sigma raised to the power of 4 I goes from 1 to n y I minus beta 0 minus beta 1 x I whole square, right. Now, our next objective is that I will try to equate these normal equations to be 0, and I will try to obtain their solution. So, if so I can do it at this step, for example. So, if I try to put it equal to 0, substitute equal to 0, substitute it equal to 0, and then I try to solve it. So, let me call this equation as equation number 1, this equation number 2, and this is equation number 3. So, the first equation, if I try to solve it, this simply gives me summation I goes from 1 to n y I minus beta 0 minus beta 1 x I, put it equal to 0, right. And this can be written as here as a or n times y bar minus n times beta 0 minus beta 1 times n times x bar, and put it equal to 0, where this x bar is nothing but 1 over n summation n x I, and y bar is 1 over n summation n y I. And now, once I try to solve it, this implies that the value of beta 0 comes out to be y bar minus beta 1 x bar, right. So, I can treat this beta 0 as the maximum likelihood estimator of beta 0, provided beta 1 is known. So, for a while, let us suppose that beta 1 can be estimated by beta 1 tilde. So, now this beta 0 tilde becomes the maximum likelihood estimator of beta 0. Well, we still have to verify whether this value will provide us the minima or say maxima. That we will try to do in the next slide. But here, if you now try to solve this equation number 2, if you simply put it equal to 0 exactly in the same way as we have done earlier, this beta 1 value will come out to be summation I goes from 1 to n x I minus x bar y I minus y bar upon summation I goes from 1 to n x I minus x bar whole square. So, I can call this beta 1 as a beta 1 tilde, and this will I will show you later on that this is also the maximum likelihood estimator of beta 1. And now, solving the third equation, we get the value of sigma square as say 1 over n summation I goes from 1 to n y I minus beta 0 minus beta 1 x I whole square. Now, this value is again going to be known only when beta 0 and beta 1 are known to us. So, I can replace beta 0 by beta 0 tilde and beta 1 by beta 1 tilde that we have obtained above. Right. So, this become the maximum likelihood estimator of the sigma square. One thing which I would like you to observe is that these thing, one is beta 0 tilde and beta 1 tilde, they are same as ordinary least square estimator of beta 0 and beta 1. If you recall, earlier using the principle of least square, we had obtained the value of beta 0 as beta 0 hat and beta 1 as beta 1 hat, and these two values are the same, right. But this is different from least square estimator. The least square estimator of sigma square, if you recall, that was 1 over n minus 2, summation I goes from 1 to n yi minus beta 0 hat minus beta 1 xi whole square. So, the difference between the maximum likelihood estimate and least square estimate of sigma square turns out to be only because of the divisor. Here in this case the divisor is n and earlier the divisor was n minus 2. Now, still we need to show that the value of beta 0, beta 1 and sigma square that we have obtained as beta 0 tilde, beta 1 tilde and sigma square tilde respectively, they are maximizing the likelihood or minimizing the likelihood. So, I would say simply that the Hessian matrix of second order partial derivatives of L star, which is the log likelihood function with respect to beta 0, beta 1 and sigma square at beta 0 equal to beta 0 tilde, beta 1 equal to beta 1 tilde and sigma square equal to sigma square tilde turns out to be negative definite. Right. This exercise is almost the same as we have done in the case of least square estimator. Right. So, this assures us that the value what we have obtained as beta 0 tilde, beta 1 tilde and sigma square tilde, they are the maximum likelihood estimates of beta 0, beta 1 and sigma square. Right. Okay. So, this is about the estimation parts. So, now you can see using two different methods we have obtained the estimates of the model parameters. The idea of taking two different estimation procedure is as follows. We wanted to show you that if you try to use any other estimation procedure, you may get a different estimator. It is only by chance here that the estimates of intercept term beta 0 and the slope parameter beta 1, they turn out to be the same. But here also you have seen that the estimate of sigma square comes out to be different. So, similarly, if you try to use any other estimation procedure, there is a likelihood or there is a possibility that you may get different estimates. Okay. So now our next objective is that how to conduct the test of hypothesis and confidence interval. So, how we try to attempt on testing of hypothesis and confidence interval estimation. I assume here that the participants will have some preliminary knowledge of test of hypothesis and confidence interval estimation, and my objective is to demonstrate here how to conduct the test of hypothesis and confidence interval estimation over the model parameters, say beta 0, beta 1 and sigma square. So, just for the sake of understanding, our model is beta 0 plus beta 1 xi plus epsilon I, and we have got n observations, and we assume here that epsilon I is normal 0 sigma square, and they are IIDs. They are identically and independently distributed. At this moment, I would like to make here a simple comment. You have seen that when we are using the principle of least square to estimate the unknown model parameters, we do not require the knowledge of normal distribution. When we attempted to estimate the parameters from the method of maximum likelihood, then we require the assumption of normality of random error components right from the first step. Now, when we are going for testing of hypothesis and confidence interval estimation, then we need the assumption of normal distribution right from the first step. Now, he will be developing the estimates of beta 0, beta 1 and sigma square. So, all those tests are going to be based on this fundamental assumptions that normality assumptions hold true. Okay. So, now in this model setup, I would say that we have here two types of possibilities. One case is that we assume that sigma square is known to us, and another possibility is that we assume that sigma square is unknown to us. Right. And then we will try to develop here three setups. One for beta 0, another for beta 1 and another for sigma square. So, we will try to develop the test of hypothesis as well as confidence interval for these three parameters under the two cases, that when sigma square is known and when sigma square is unknown. Right. So, first of all, I try to consider the case of slope parameter. And my null hypothesis is H naught, say beta 1 is equal to beta 1 0. This beta 1 0 is some given constant, and this is assumed to be known. Before going forward, I would like to inform you that this test of hypothesis and confidence interval estimation, they play a very important role in getting a good model. Later on, you will see that through testing of hypothesis and confidence interval estimation, we try to judge whether a variable is important or not. So, this is very important for us to understand that how we are going to develop the test and under what type of conditions we are going to use it. Okay. Now, you can recall that you had estimated the slope parameter by Sxy upon Sxx, and that was in both the cases, whether it was ordinary least square estimation or this was method of maximum likelihood estimation. Right. So, now I try to consider the first case, that when sigma square is known. Right. So, under this thing, since we have assumed that expected value of epsilon I is 0 and variance of epsilon I is sigma square. So, based on that, we have demonstrated that expected value of beta 1 hat is beta 1 and variance of beta 1 hat is sigma square upon Sxx. These are the expression that we had obtained earlier, and we had also shown that beta 1 hat is a linear function of y's, and y's are following a normal distribution with mean beta 0 plus beta 1 xi and means and variance sigma square. all this information that we already have established. So, now I can write down that since beta 1 hat is also a linear function of yi, so beta 1 hat also follows a normal distribution with mean beta 1 and variance sigma square upon sxx. Right. So, based on that, now I can create here a statistics. So, now I can write down here that beta 1 hat minus beta 1 0 divided by square root of sigma square over sxx, that we know this is going to follow a normal distribution with mean 0 and variance 1, right, when H naught is true. So, let me denote this statistics as Z1. So, now Z1 is the test statistics that can be used to test the significance of slope parameter when sigma square is known, right. So, this test statistic can be used to test the significance of beta 1 when sigma square is known. Right, how to get it done? So, we know that in the case of test of hypothesis, if I try to draw the distribution, the entire quick distribution is divided into two parts, right. One is critical region, and another is, say this here, acceptance region. Okay, and this is here the mean 0, and this is the curve of normal 0 1. So, now depending on the alternative hypothesis, I can frame here different types of decision rules. Right. Suppose my alternative hypothesis is beta 1 greater than beta 1 naught. Okay. So, in this case, the rule is reject H naught if Z1 is greater than Z alpha, right, where alpha is the level of significance. So, this region here is actually alpha, and this region here is 1 minus alpha. So, if we try to calculate the value of Z1 and we try to see if the value of Z1 is going to lie in this region, we accept it, and if it is going to lie in the critical region, then we reject it, right. And here this Z alpha is the upper alpha percent points on the normal 0 1 curve distribution, right. Next, I try to take another case, in case if my H1 is beta 1 less than beta 1 naught. So, in this case this normal 0 1 curve will like this, and but the critical region is going to be on left hand side. So, this is our critical region, and the size of critical region that we are going to consider, this is alpha. So, this is your acceptance region of size 1 minus alpha, acceptance region. And in this case, I would say that reject H naught if Z1 is less than Z alpha. The third case will be that we try to consider here H1 is, say here beta 1 not equal to beta 1 naught. In this case, the normal 0 1 curve will have the critical region on both the sides. This is our critical region, this is our critical region, and this is our acceptance region. And this is of size alpha by 2, this is of size alpha by 2, and this is of size 1 minus alpha. So, these are the points which are minus Z alpha by 2 and this is the point which is z alpha by 2, because the mean lies over here, right. So in this case I would say that reject H naught if Z1 mod of Z1 is greater than Z alpha by 2. So this is how we are going to take a decision, right. So we stop here, and in this lecture I have tried to explain you in detail that how we are going to construct a test of hypothesis. We have considered the case for the test of hypothesis H naught beta 1 is equal to beta 1 naught, and I have given you the development of the statistics and how to take the decision on 3 types of alternative hypothesis. Now I will try to take some more cases, for example when sigma square is unknown, and then the test of hypothesis based on intercept term and sigma square in the next lecture. Till then, goodbye.